Hola, my name is Pamela. Welcome to my channel. Today I'm gonna talk about invented by the French engineer Henri Pitot in 1732. The Pitot tube measures the difference between the total pressure and the static pressure, that is, the dynamic pressure, which is proportional to the square of the velocity. A velocity coefficient c can also be added to account for uneven velocity distribution, pipe roughness, etc. Pitot tubes can be found in speedometers, manometers, and anemometers, which are used to measure wind speed. Among its features is requires laminar flow, because it is sensitive to variations in the velocity distribution in the pipe section. To measure with maximum accuracy, it measures at different determined points and averages the square roots of the measured velocities. The impact hole of the Pitot tube should be between 0.25 diameters over 2 and 0.29 diameters over 2 from the inside wall of the pipe. The sections of pipe before and after the tube must be straight enough. They have an accuracy of the order of 1.5 to 4%, typically used to measure large flow rates of clean fluids with low pressure drop. The Annubar tube is an innovation of the Pitot tube and has two tubes, one to measure the total pressure and the other to measure the static pressure. The first is located along the transverse diameter of the pipe and consists of several holes of equal diameter whose position is determined by computer. The second tube is behind the first one downstream and has a hole in the center. The Annubar tube is more precise than the Pitot tube. It has a low pressure drop and is used to measure small or large flow rates of liquid and gases. These instruments have the function of integrating the flow of a graph, which is required for building or the energy balance of the plant. There are three types of integrators: mechanic, pneumatic, and electronic or digital. For liquids, the density variations depend on temperature, and in gases and vapors on pressure, temperature, and compressibility. Therefore, if all these variables are registered in the same graph and the corrections are calculated, we can obtain the real flow. Automatic compensation is achieved with a multiplier divider instrument for the differential pressure, temperature, and pressure variables. The differential pressure created by the orifice plate, nozzle, or venturi tube can be measured with a mercury U tube or transmitted with differential converters. These transmitters measure differential pressures and how the flow varies according to the square root of the differential pressure. The transmitters that I will mention can use pneumatic force balance transmitters, electronic force balance transducers, or digital diffuse silicon or capacitive transducers, depending on the variable to be measured. If you want to know more about these transmitters, I will leave you the video where I explain them more thoroughly right here. There are two types of differential pressure transmitters: the bellows and the diaphragm. The bellows have a chamber for high pressure and another for low pressure. The high pressure compresses the bellows, which drives the joint lever, the cable, and outer shaft, whose movement acts on the pneumatic or electronic transducer. A margin spring allows for various differential pressure ranges. Protection against overloads is ensured by two seal rings that hermetically close the passage of the filling liquid from one bellows to another and prevent its destruction by incorrect operations. It also has an anti-pulse flow valve that restricts the flow of filling liquid between the bellows. The diaphragm ones are similar to the bellows ones, with the difference that the chambers are separated by diaphragms instead of bellows, which means that the volumetric displacement is almost zero. The body of these transmitters is usually made of carbon steel, stainless steel, or aluminum, while the bellows or diaphragms of 316 gauge stainless steel, being silicone the filling liquid. The connections between the diaphragm tabs and the differential pressure converter must be suitable for the fluid to be measured. To isolate the instrument, three valves are foreseen, and they constitute what is called a manifold, which isolates the instruments from the process for its maintenance and equalizes the pressure in the two chambers at the start of the installation. When the fluid is corrosive, viscous, or changes its state, it is necessary to use seal systems to isolate the instrument from the fluid. In these systems, 50% glycerin and 50% water are commonly used. For both types of transmitters, it is important to take into account whether the process fluid is susceptible to condensation, solidification, or freezing at the lowest temperature found in the pipes, since if this is the case, it is necessary to have a heating system, which can be electric or with low pressure steam. If the piping is subject to strong vibrations, it is preferable to have flexible connections between the instrument and the system. When the problems of condensation, evaporation, or clogging of the element cannot be solved, it is necessary to have a purge system that introduces a purge fluid into the measurement area of the differential element. The purge fluid must be clean. It must not react with the fluid to be measured, it must circulate at low and constant flow rate, and there must be a system that prevents entry of the process fluid in the event of purge failure. And well, this will be all for today's video. Don't forget to give me a like and subscribe. I upload videos every Wednesday in Spanish and Friday in English. Adios! A velocity coefficient